But forget everything you know about modern insects.
Forget everything you know about modern insects.
This world existed over 300 million years ago.
Over 300 million years ago.
Welcome to the Carboniferous Period, the Age of Giants. But the real marvel wasn't the plants, it was the arthropods. But insects and their relatives grew to unbelievable sizes here. But giant dragonflies, the size of modern hawks, dominated the air. But their wingspans sometimes exceeded 2 feet across. And now that we understand the scale, let's explore why. The secret lies in the air composition of that lost world. Modern insects breathe differently than vertebrates do. They use a passive system called trachea tubes. Gases diffuse directly into their tissues, limiting body size. But during the Carboniferous, oxygen levels soared dramatically. Estimates suggest atmospheric oxygen reached nearly 35%. But this dense, oxygen-rich air could penetrate much deeper. This eliminated the crucial size limitation for terrestrial invertebrates. Imagine terrestrial creatures weighing several pounds, moving freely. The massive forests themselves were the engine driving this phenomenon. Giant club mosses and tree ferns covered the world back then. These plants photosynthesized relentlessly, locking away carbon dioxide. The wet, oxygen-poor swamps prevented full decay, forming coal. This massive carbon burial released huge quantities of free oxygen. This elevated oxygen fueled a giant arthropod arms race. The largest of these predators was the colossal griffin. With jaws capable of crushing bone, it reigned supreme. It hunted smaller, yet still huge, prey moving through the understory. Below, vast sheets of armored millipedes crawled everywhere. These creatures reached lengths comparable to small cars today. Their large bodies required incredibly efficient oxygen intake. The high oxygen saturation meant high energy output was possible. Now that we understand the ecological drivers, let's consider the end. This aerial paradise was inherently unstable, destined to change. Tectonic activity shifted, causing climate cooling across the globe. As temperatures dropped, the massive swamp forests began to shrink. A less plant life meant less photosynthetic oxygen production. The atmospheric oxygen levels gradually fell back toward modern percentages. But this atmospheric shift placed an immediate, inescapable constraint on arthropods. The diffusion pathways that once supported giant bodies became inadequate. The giants could no longer sustain their immense bulk. Evolution favored smaller, more energy-efficient body plans once more. The constraints of modern atmosphere reasserted themselves swiftly. We see the legacy of that oxygen spike in modern insect size. The upper limit for flying insects is strongly linked to oxygen partial pressure. The remnants of that giant world fuel our current civilization. At every lump of coal is stored potential from that high oxygen era. The entire global system was balanced precariously on this gas ratio. Our fossils offer tangible proof of these bizarre, temporary conditions. Imagine the sheer biomass required to maintain that level of oxygen. On Earth's atmosphere is not static, it is a dynamic, living system. But even the smallest environmental factor can radically reshape life. On today, we live in a world where oxygen is tightly regulated. The size ceiling for our current atmosphere is quite strict. It defines the maximum metabolic rate for terrestrial invertebrates. The Carboniferous giants were an evolutionary detour, a brief anomaly. A world where air allowed insects to fill niches reserved for birds. Of this period demonstrates life's profound dependence on its chemical surroundings. The giant bugs were just one symptom of a planet supercharged with oxygen. Creatures thrived at sizes that defy easy comprehension today. The atmosphere eventually returned to balance, taking the giants with it. Understanding the air means understanding the true scale of ancient life.